a chi-square. So we learn it. We learn how to use it. Unfortunately, again, there's no calculator for this. It has a chi-square test, but it is not this one. So we have to do this by hand. I will give you the formulas. I have no problems giving you these formulas. I don't expect you to memorize them. But I just need you to know how this works. So just as we started with the point estimate for your sample mean, we do the same thing here. We say population, sample. Your population variance is this. It's sigma squared. Your sample is S squared. Your standard deviation, this is for your variance. And your standard deviation, write this down somewhere because this is important. You need to know this. And that's for your standard deviation. Okay? Just on the note page that I gave you. If it's not there, you can put it on that page. But you have to know that this are the point estimates that we use. We only get information from our sample, as we did for the rest of the intervals. We use our information from our sample to make an inference about where we think our population parameter would fall. And in this case, we're going to do variance and standard deviation. So just so that you remember the symbols for these guys. And I'm pretty sure I put them on your notes, but underline it, make a little chart. Chart kind of stands out a little bit better. We use a chi distribution. It's a series of curves, and it's going to change. We're going to get two different numbers this time to work from, because these are all positives, and the area in the table is to the right of what we're looking at. This is another problem. We read this table very differently. All our other tables are area to the left. This is area to the right. So this one we kind of keep totally separate. It's its own little animal here. Let's go through and see what we come up with. This is the formula we're going to be using. We'll go through this. God bless you. Does this look familiar? Remember doing this at all when we subtract 1 from the sample size? What did that give us? Degrees of freedom. This is your degrees of freedom. Look at your chi-square chart. Doesn't it say degrees of freedom? Look how easy this looks. Creepy, but it's so easy. This is your variance from your population. This is your variance from your sample. Okay? So, not so bad to have to use this. We're going to play with this a little bit, but basically it's going to look like this. So we're going to have all your chi-square values, that little x, that special little x, are going to be greater than or equal to 0. They're all going to be positive numbers. They can be 0. The chi-square distribution is determined by the degrees of freedom, where everybody has a choice of freedom except that last one. The area under the curve, no matter what it looks like, still is equal to 1. That one stays. They're positively skewed, means they're skewed to the right. They're skewed to the right towards the positive numbers. And therefore, their distribution is not symmetric at all. The chi-square is different for each number of degrees. And as the number of degrees of freedom increase, the chi-square approaches a normal curve. Approaches, but never really kind of gets there. Okay? It's less scary when we finally get to do this. Now, here's the important part. This is probably the most important part. You'll need to find 2 critical values each time we do this, for each level of confidence. We have a critical value to the right. We have a critical value on the tail to the left. So we call it, using their x, x2r, x2l. This is for the variance. So we have one for the left tail, one for the right tail. That's what we use table 6 for. Remember table 5 and table 4? We only found one variable. Blue could be a negative, but we always use the positive in our E thing. Remember the 8? and we either had a ZC or we had a TC. And we always look up the area to the left and we put the positive in here. This one works totally different. We're going to have to do two different things. And this one, it's always area to the right. I do mine a little bit different than the book does, just because the book tends to be a little bit confusing. And I'll show you how I do it in a second. But they have two formulas, one for finding the one on the right, one for finding the one on the left. But I'm going to do it a little bit different than they do it. Again, we're still going to do your, when we say 90%, we're still going to do 1 minus 0.90 divided by 2. We're still going to do that, okay? Just like we do for the other ones. But the area to the right is going to be opposite of what we expect. So we're going to play with those numbers. So let's find them. All right, so we need to find the critical values for the left and the right for a 95% confident interval when my sample size is 18. If my sample size is 18, what's my degrees of freedom? 17. Now, notice your table 6. It's got the degrees of freedom. Notice across the top. I really, even though I see a 0.95, I see a 0.995. Like, how did I get a 0.995? It couldn't have come from this, right? So it has to come from somewhere else. So I start like this. I say, okay, I'm going to make myself a little skew here. I'm going to get a critical value left and a critical value right somewhere. So I say, okay, this is my left-hand guy. Makes sense. This is my right-hand guy. Left, right. Great? So we're going to start like this, regardless of what the formula says. We know our old favorite. We go like this. So this gives me 0.05, right, divided by 2 is equal to 0.025. Agree? Okay, so now, since my area adds up to 1, what is 1 minus this guy? 0.975. These are the guys I want to look up. Regardless what their formulas say, these are the guys I want to look up. 0.025, 0.975. Now, in the book, they go through the formulas. We're only doing one formula. We're only doing our favorite formula that we've always done. I don't want you to reverse it. Because then what happens after you reverse it with the plus, you forget when we go back to the table 4 and table 5. So I only do this one, like we always do. Now, when you go to your chart, pull out 17, go to 17, pull out the 025 and the 0.975. And just write them down for a second. Pull out your 17, go to 0.975. What do you get? Okay. Go to 0.025. Notice as you get smaller in there, you get bigger numbers. So now, mindlessly we say, which one is the smaller number? 7.5. So if this guy actually goes from 0 to infinity, my 7-point guy is this one. Right? Because this should be higher. So did I really have to keep track of who is my left and who is my right? I just say, take this, do what we always do, get this little number here, and then subtract it from 1. Again, your chart is symmetric. Your chart is symmetric. If you draw a little line between 0.90 and 0.10, it goes 0.90, 0.10, 0.95, 0.05. You'll see symmetry. You don't really even have to subtract it from 1. You'll see that even though the graph is not symmetric, your chart is symmetric. So if you look at the top where it says 0.90, 0.10, and you draw your line, there's your symmetry, like this. So this says 0.95, this says 0.05. These numbers always match up. And all we have to do is say, okay, take the smaller one that goes on the left. The larger one goes on the right. because that makes sense when my numbers go from 0 to infinity. Okay, so I don't want you to worry about their formulas. So let's find another one. I need to find my critical values. Again, I'm coming from the left and the right. Okay, so I have a 90% confidence interval when my sample size is 30. What's my degrees of freedom? Okay, I do the same way I always did. 1 minus 0.90 divided by 2. You can do it in your calculator. 1 minus 0.90 gives me 0.10. Divided by 2 gives me 0.05. If I do 1 minus 0.05, what do I get? 0.95. So these are the two guys I'm looking up. I need my X2L. I need my X2R. My smaller number goes on which one? The left. So I look up in my chart, degrees of freedom 29. I follow which one's going to come first on the top left, 0.95 or 0.05. Look across the top. 0.95, because you see your numbers in the graph, they keep getting larger. So 0.95, it's the opposite of what you think, because the area is to the opposite side. But that's okay, we don't care about that. We're just going to go there and say, oh, that has to be smaller than when I hit the 0.05, right? So the first one I hit, 17,708, is my left. I need the smaller number on my left because these numbers go from 0 to infinity, and they're always positive. I keep going till I hit 0.05, and I get 42,557. Good. This is the hardest part right here. That's it. Not bad, right? That's the hardest part to this. Okay, so we okay finding this? All right. Now, we're going to put this together into this lovely formula. Yes, it looks horrible. However, let's break this apart. This is your degrees of freedom. That's easy to find out. This is your sample standard deviation. Well, that's something they're going to have to tell us, right? This is my X2R. You just found that. My X2L, you just found that. So really, that's not so bad. From here to here, all they did was take the square root. Because the variance over here to the square root says, if I take the square root of this, don't I get my standard deviation? So this is my confidence interval for my variance. I don't have to rework this out. I just got to take the square root of those numbers. There's my confidence interval for my standard deviation. That's it. That's how simple it is. It's horrible to look at, but it makes a lot of sense. The hardest part you're going to do is find these. Now, I want you to notice one other thing. You found your X2L, which is the smaller number, right? And the X2R is the larger number. In the formula, they put the X2R first. So say this. Say my X2L is just 2. Say my X2R has to be bigger, is 5. If I put my left over here, and I put my right over here, when I divide by a smaller number, don't I get a larger number? So this wouldn't work in this inequality statement. So therefore, I want to divide by my larger number to get the smaller number, divide by my smaller number to get the larger number to make my inequality work. And I have kids that put it backwards, but as soon as they make their inequality, they say, oh, that can't be right. Just swap your numbers in your inequality. You'll see it as soon as you do it. Okay, so it looks very scary, but it's easy to work with. Ready to try one? That's how easy this one is. It just goes against what we normally do. This area to the right, which I don't want you to get hung up on, which you kind of see it in your chart, the way that the numbers go. I still don't want you to get hung up on which area goes where. We do it my way, so we keep consistency there. Again, you're going to verify that your population has a normal distribution. We do all the same things we've always done. We're going to identify your degrees of freedom from your sample size. We're going to find a point estimate. In this case, the point estimate is our sample variance or our sample standard deviation, whichever one they give us. Sometimes they give you a sample standard deviation. If they give you a sample standard deviation, then in the formula, you have to put the square next to it. If they give you the variance, you don't square it because it's already squared. You're going to find your endpoints. This is your x2L and x2R. And then you're going to plug everything into this formula. There's your interval for your variance. We're going to take the square root, well, whatever numbers those are, and we get our interval for our standard deviation. Okay. Everybody panics over this, but then after we do it, they say, that was the easiest one. Okay, so this is on page 333. You notice they don't even give us just these two problems to do, and then you're done. So it's not really that big of a deal or that big of a unit. It just is different. And I really, really, really don't want you to get hung up on the differences. And right after this, we go back to z-squares, and that will just mess up if you think the wrong way. Okay, so you randomly select and you weigh 30 samples. What does 30 samples mean? What variable is that? N. So what's my degrees of freedom right away? 29. You randomly select and weigh 30 samples of an allergy medicine. Now, if you're taking an allergy medicine, are you comfortable knowing that you don't have the exact amount of medicine? Like, should your medicine vary by that much? No. So your variance on your medicine, anything medical, has to be really, 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 really tiny. It's not healthy, it's not safe to give you either over the amount or under the amount is not going to help your allergies. So they have to make the exact values and have as a little bit of its variation as possible. Assuming the weights are normally distributed, all right, so I need to know this about my population, the sample standard deviation. I've got a sample, and I write that with an S, is 1.20. Construct a 99% confidence interval for my population variance and my population standard deviation. So my point estimate is this guy. This is my point estimate. So again, I'm going to start with, okay, here's my curve. It goes over here somewhere. I have an x2L and I have an x2R somewhere. I need to find those values. So I start with 1 minus 0.99 divided by 2. This gives me 0.01 divided by 2. This gives me 0.005. What is 1 minus 0.005? 0.995. Good. So find me the x2L and the x2R using your table 6. So table 6 says find the lesser one first, so you got to look up the 0.995 because it's opposite. It's area to the right, but don't get hung up on that. Just take the two numbers. Whichever number is smaller goes on the left. Whichever number is larger goes on the right. This goes from 0 to infinity. So find me the smaller of those two numbers. Good. I think that vacation was good, huh? Came back all refreshed. The one on the right. Yeah. You got 42. Did you look up 0.005?
Oh, my fault. 52.3.
Okay. Remember, your chart is symmetric. So if you're on the very end of one, you're going to be on the very end of the other. The graph is not symmetric, but your chart is. That's half your battle. So now we use your formulas. we have to do is plop this in. Our degrees of freedom, that was easy. 29, 29, 29. Our standard deviation, 1.2. I know this guy. I have to take the standard deviation and square it. Don't forget to square the standard deviation. I'm going to rewrite this in a second. So we're going to say 29 times 1.2 or 1.20 squared over my R guy. My R is my bigger number. Remember, we want to divide first by the larger number to keep this inequality correct. Then we're going to say 29 times 1.20 squared over my smaller number. This will give me a larger answer. And you can do those parts right in your calculator. You don't need any extra. Some of you question how to do the calculator. Nice and easy. Put this one in just like you read it. Just say 29 times 1.2 squared. Use your square. Divide by. You don't need any extra parentheses. 52.336. It didn't multiply. Thank you. Of course it didn't. Okay, better. Okay, now I want you to round to whatever the standard deviation or the variance is rounded to.
On the board there, the next to n minus 1 on the first row, what does that say next to?
S squared. I just took the formula. S squared. Just since we have a standard deviation, John, we have to square it. And I'll show you the difference between us and giving us a variance. So I'm going to round this to 2 decimal places. And I'm going to round that guy to 2 decimal places. This is my confidence interval for my variance. I can be 99% confident that my population variance of all the allergy medicines will come between 0.80 and 3.18 of centimeters or whatever things they were measuring here. Okay, now, how do I get my standard deviation? I don't have to redo anything. All I have to do is take the square roots of these guys. That's it. So I take the square root. When you take the square root of a decimal, you actually get a larger number. If you take the square root of something less than 1, you get a larger number. I make that be standard deviation, and I take the square root of this guy. That is my confidence interval for my standard deviation. It's that simple. Okay, now the only problem is this. If this problem gave you the variance instead of the standard deviation, so say they said the sample variance, I'm just going to say is equal to 3, then when you come here, you're just going to put the 3 in for this whole thing. You're not going to square it because the variance is already squared. The S represents your standard deviation, squared represents your variance. So if they gave you a variance instead of a standard deviation, we would just put it in and not square it. If they give you a standard deviation, you're going to square it. Try 2. Everybody work on the next one. You try it 2. You have about 5 minutes. We can get it done. Just do the 90%. I'll tell you what. This group over here, these 3 rows, do 90%. These 3 rows, 95%. Because the problem is this. You don't have a calculator to do this, so you have to recalculate your values first. You have to recalculate those. So it's a lot of calculation. So we'll have you guys do part of. On the 90, did anybody find me the X2L, the X2R from this group? Anybody find the X2L? Okay, the X2L is 17.708, so I'm going to put it over here. Thank you. What's the X2R?
42.
Good. So I'm going to put that over here because remember we want to just divide by the larger number. Doesn't that make sense? So this becomes the smaller part of our inequality. And this breaks down to 0.98 and 2.36, right? Take the square root of these guys. That's your confidence interval for your variance. And anybody get this for the, did you take the square root of this? Where's my group working over here? Okay, that's because you didn't know how to round this, right? 0.989. So if I got to round this here, this is going to go to a 9. And square root of 2.36. 1.54. Okay? The rest stays the same for these guys. Anybody find me an X2L, X2R for this one? There's your X2L. There's your X2R. 45.722. And what's this guy? 16.027. Good. So when we do this, I have 3 decimals. I'll just take 3 decimals out. And then you're just going to take the square root of these guys. Okay, so we can see as we need to be more confident, our interval gets a little wider. And 99, the one that we just did, gave us the widest one. That's all there is to this.